In this video, I'd like to go over example 4-6, and this is on page 191 in Elements of Chemical Reaction Engineering in the 4th edition by Fogler. And I'm pretty sure that this example is probably in Essentials of Chemical Reaction Engineering as well, but I'm not sure if it's on the same page. So anyway, this example is calculating conversion or X in a reactor with a pressure drop. And the reason why I want to go through this example is because in the book they use Polymath to solve the two differential equations you get. And so I would like to go through and do the same thing, only solve with MATLAB instead of Polymath. And so far the problems we've been solving, you've been able to simplify your differential equation enough to where you can get an analytical solution. But as we go further along and you can't make as many assumptions, or maybe you're solving more equations, like more than one equation, then you need to use an ODE solver to solve your equations. And if you're not familiar with MATLAB, I actually recommend using Polymath because I think it's a little more straightforward as far as how to enter your equations. But if you want to use MATLAB or you're familiar with MATLAB, then I want to show you how to do this problem in MATLAB. And you can also use Aspen. I've never used Aspen. I've only used MATLAB and Polymath, and I've used COMSOL. I don't recommend using COMSOL for this. So, but basically you just need to pick a solver and use it to solve these problems. I don't think the class is telling you a specific solver you have to use, so you can just pick what you want. So first of all, I wanted to go through the problem just to show you where the equations come from that we're going to be solving. And as always, this just follows the same setup as, or the same algorithm as all the other problems we've been solving. So this is what we're given. So we have ethylene and oxygen, and we're forming ethylene oxide. And what we want to do is calculate, and we're using a packed bed reactor, and so we want to calculate the necessary catalyst weight to get at least 60% conversion. And so we're given the FA0 is 0.3 pound-mole per second. The pressure is 10 atmospheres, and we're also told that we actually have 10 banks of PBRs and of the packed bed reactors, and it tells us that each tube is a 1.5 inch diameter schedule 40, and that each bank has 100 tubes. So really we have 1,000 tubes. And so what that means is FA0 is actually the given FA0 divided by 1,000. So this is per tube, this is total. And the properties of the reacting fluid are identical to those of air at this temperature and pressure. The density of the catalyst is 120 pound per foot cubed. The diameter of the catalyst is 1/4 inch. The void fraction is 0.45. And then it gives you the rate law, which is K PA to the 1/3, PB to the 2/3. The rate constant is this. And so then we just start this problem like any other problem. We first of all do our differential mole balance, and so we have to use the differential mole balance here instead of and it has to be in differential form and not integral form. And the reason why is because we have a pressure drop. And so if you either have a pressure drop or a change in temperature, or like if there's a heat exchange, then you have to use the differential form of the mole balance. And so this is the mole balance for a PBR. And this is from chapter 2. And then it gave us the rate law. So we want to, since we were going to end up getting the concentration of A and concentration of B, we actually want to put it in terms of concentration, and we can do that because we know that P is equal to, well, PA is equal to CA RT, and PB is equal to CB RT, so we can just plug those in, and then we end up getting this. And so then we do the stoichiometry. We know it's gas phase and isothermal, so this is chapter 3. So concentration is equal to the molar flow rate over V, and this, so then we end up getting this. So FA is equal to CA naught 1 minus X, and so this is, it would actually be FA naught 1 minus X over this V would be V naught plus, or multiply V naught 1 plus epsilon X, and then we would have the FA naught over V naught, so we get CA naught. And then since we have a pressure drop, that's multiplied by P over P naught. And then we can take this a step further and say that P over P naught is equal to Y. And then CB, this is basically get it from the same table, so CA naught, and this time we have theta B minus X over 2, and I put the B over A here just to remind you that this is actually theta B minus B over A multiplied by X, and then B over A is 1/2 multiplied by 1, so that's why that's divided by 2. And then this is over 1 plus epsilon X multiplied by Y, which was the P over P naught. And then theta B is equal to FB divided by FA naught. This is actually FB naught divided by FA naught. And that equals, so, and it tells us in the problem that it's fed in stoichiometric proportions. So we know that the theta B is 1/2. And so then this ends up being equal to, well, so if we plug in the 1/2 and then we pull out the 2, then we get this equation. And then for the pressure drop, we're going to use the Ergon equation. And so this is the form that we want to use. And so this is for pressure drops, isothermal in a packed bed reactor. And so when you use this equation, just make sure that you're using the correct form of it. And it goes over this in chapter 4. So then we can go ahead and combine some things. And before I go into combining, I just want to point out, since we're going to solve this numerically with MATLAB, we don't actually need to go through and combine these. We could put this equation in, this equation, these are the two differential equations we're going to solve, and then we could put in what RA prime is, what CA is, what CB is, and then all these constants. But in the problem statement, they go through and evaluate these, so I'll just go through it. So for the rate, they just put CA and CB into this equation. So then we get this, and you can pull out for this one, if you pull out 1/2, 2/3, then you can combine these two to get just CA naught 1 minus X over 1 plus epsilon XY, and then multiplied by 1/2 to the 2/3, and then we still have the KRT naught. And we know that KRT naught multiplied by CA naught is equal to PA naught. Well, actually, sorry, not the K, just the RT naught, CA naught is equal to PA naught. So then you can plug that in, so you get K PA naught is equal to 1/2 to the 2/3 multiplied by this, and then you can define this. So they just defined a K prime, which was 1/2 to the 2/3 is 0.63 multiplied by K PA naught. And then we need to evaluate the parameters for the tube, and we already know that everything. So these basically just all need to be divided by 1,000 because they were, so, and we already did this here, so FA naught is, well, so we know that this was the total FA naught, and then, but then we know that we have 1,000 tubes, so dividing by 1,000 we got this. And then we want to convert that to pound mole per hour. And really we're just putting everything into the same units, so when we solve these two differential equations, the units work out. So that's, you just want to make sure that everything is the same units before you start putting things into your program. So, and then FB naught is 0.54 pound mole per hour, and because it was half that. And this is the inerts, and it was 2.03 pound mole per hour. And then the total FT naught is all of those added together, so you got 3.65 pound mole per hour. And then we need to calculate PA naught because we have it here. So PA naught is equal to YA naught, the mole fraction of A, multiplied by the total pressure. And so the mole fraction of A is 0.3, and I believe that was in the, yeah, because FA naught over FT naught. Is that right? So this is right. So FA naught, which is 1.08, divided by FT naught, 3.65, and plus, well, okay, so yeah, so then epsilon is equal to YA naught delta, so 0.3 multiplied by 1 minus 1/2, that equals negative 0.15. So then you can plug those back into this PA naught, and you get YA naught, which is 0.3, multiplied by P naught, which is 10, so you get 3 atmospheres. And we can also calculate what K prime is from this. So we know K, we know PA naught, and so doing that you get 0.0266. Oh, actually there's more on this page. So then we need to calculate the pressure drop parameters, and I didn't go through this in detail because it's basically just plug and chug once you have the equations. So you should go look at the example 4-6, and then they calculated an example 4-4. So you can look at example 4-4 to see how this was calculated. But to calculate alpha, we need to know beta naught, and we know everything else. So beta naught was 0.0775 atmosphere per foot, and then alpha ends up being equal to 0.0166 per pound mole catalyst, or per pound catalyst. And so then you can kind of start combining, well, writing down your equations that you're going to solve. So these are the two differential equations, and then these are the constants that we need to solve these. So K prime, FA naught, alpha, and epsilon. And then in order to solve this, we also need some boundary conditions. So we're going to use the W equals 0, there's no conversion, so X is equal to 0. And also at W equals 0, there hasn't been any pressure drop yet, so P naught is, so this Y equals P over P naught, and so P at W equals 0, then P equals P naught, so then you end up with Y equals P naught over P naught, which is equal to 1. And then we also need, in order to solve this problem and numerically, we also need to put in a final weight. And so we just guess what this is, and so we know that we want about 60% conversion. So say we put in 30 pounds and the conversion ends up being too low. Like, I don't know what it would actually be, but say it ends up being 40. Then we know that the weight we put in was too low, so we just try a higher weight and solve the problem again. And you can keep incrementally increasing your weight until you reach the conversion that you're expecting. And then they also looked at this parameter, like in the example, they looked at this parameter f, which is basically the change in volumetric flow rate over the length of the reactor. And so that's just something interesting that you can look at, basically how the volumetric flow rate changes across the length of the reactor. And so now, and I went through this problem really fast because it's in the book, and so you can go look at how this was set up. And so now I want to look at the MATLAB code. And so you need to write a couple files to solve this in MATLAB. First of all, you need to write, so that's the script. So the first thing you need to write is a function that solves the right-hand side of the equation. And so that's what I've done here. So I'll just pull up this, let's see, minimize that. Just want to pull up this page with the equations so you can look at the equations while we look at the function. Okay, so this is a function. Oh, and then, well, first I'll talk about the function because this is going to be the same pretty much for any solver in MATLAB. So first of all, you need to write a function that solves the right-hand side of the equation. So for this, I have dy dw, and you can call that pretty much whatever you want, equals PBR, and then I have the independent variable and the dependent variable. And in this case, we actually have two equations, so there's two dependent variables, but in MATLAB, you're only allowed to have one variable, so you have to do what I've done here. So I set up basically an array with, so this has, hold on a second. I'll show you what that looks like. So dy, oops, dy, dw. Oh, never mind, because I can't do that because this is in the function. Okay, so, well, I know what I can do though. All right, so this is, I guess this is a vector with 2 rows and 1 column. And so this will be used, this is our 2 dependent variables. So the first one is y1, so x is equal to y1, and y, which is the pressure drop, is y2. And so then I put in the constants, and those were, epsilon was negative 0.15, k fa naught, alpha, and then I calculated Ra prime. And so this is what I was talking about earlier. You could, once you had these equations, you were pretty much set as far as starting to program this. You would just need to, so the way I put this in is I have my first equation, so dy dw1, which, so this is actually dx dw, but I can only, since I can only have the one variable, I just call it y, and so then that's just this equation. So dx dw equals minus RA prime over FA naught, and so I just put that directly into here, and then I have RA prime here, and let's see here. Yeah, so so the reason why I like doing it like this is then this code is, like if I put this in for dx dw instead of this, I can easily reuse this code for other problems, because all I need to do in the future is change RA prime and change the values of these constants, or put different ones in depending on what I need. But I should be able to just type in, like if I have it like this, then I can just type in, okay, I know what FA naught is, so I change that, and then put in my new equation for RA prime depending on, or for the rate depending on what your rate is. So I just wanted to point that out, that you can put this equation in or do it like this. And so then for this dy dw2, this is actually, well, this is dy dw, which is the pressure drop. And so I put this, I mean, this equation is the, I didn't change anything in this equation between here and here, so that just went in how it is. And then when you're referring to, because of how this is set up, when you're referring to your variables, so when you refer to x, you have to put y1, and when you refer to y, y2, so you can see that here. So like this one, well, so this one I have minus alpha 1 plus epsilon x, so x would be y1, and then it's divided by 2y, and so 2 times y2, because that's y. And so then once you get this set up, oh, and then the other thing with the functions is this has to be named. So whatever you call it here, it has to be named the same. So I have PBR for packed bed reactor, so then this has to be PBR.m. And you have to make sure that that's named the same as this, otherwise your function isn't going to work. So then the way you run this is you write a script, and so I have, so this is w, which is the independent variable, and then I have y, and remember this is that vector of x and y again. And then I'm calling, so this is one of MATLAB's built-in ODE solvers, and they have a bunch of them, but I almost always use this one. The only reason you wouldn't use this one is if for some reason you have a system of equations that you can't use this, and I know that sounds abstract, but if you really want to know, you can go read about it some more, and mostly what we're going to be solving in this class, you should be able to use ODE 45. And so some of the other popular solvers in MATLAB, there's ODE 23, and then there's also dsolve. And so dsolve actually attempts to solve your problem symbolically, and I haven't used dsolve all that much, so I don't know how well it actually works. And so anyway, so for, and yeah, ODE 45 is explicit Runge-Kutta. So if you know what that is, if not, don't worry about it. And so the way you call this function is you put in, this is the right-hand side of your equations, and it gets those from the function that you wrote here. So whatever you called your function for the calculating the right-hand side, you would put in here. And then this is your initial and final, or I guess your boundary conditions for W. So we start out at W equals 0, and then W final, we're going to guess 60. Well, I mean, I already know it's 60 because that's what they came up with in the example in the book, but if you didn't know 60, you would just have to guess something and then see if you got your expected conversion, and if not, then you would change it. And then this is your initial value for conversion x, and so that's 0 because there's 0 conversion at first. And then this is your initial value for y, which is p over p naught, so the pressure drop, and initially it's 1 because there hasn't been any drop yet. And so this right here calculates x, your conversion, and the pressure drop for w. And you could just go down here and so for this first plot I'm plotting the weight versus x conversion. I'm plotting the weight versus y, the pressure drop. And then I also wanted to plot this F, because they did in the example, which was the change in the volumetric flow rate over the length of the reactor, and then also, or actually over the weight of the reactor, but yeah. And then the weight versus rate. And so I did some extra calculations here just to calculate that. And so I just want to show you real quick the way you would reference what you get back. So for instance, RA prime, I'm calculating, let's see, where is that again? So yeah, for RA prime, this is the equation that we have here. And I have minus K prime, which was this, multiplied by 1 minus x. And so the way I reference x is I get back y, and I'm actually going to run this real quick so I can show you what you get back. So let's close that real quick. So if I go in here and type y, then this is, you can see what you get back. So, and these are the initial values you gave it. And so this first column is x, so this is your conversion. And the second column is y, so this is your pressure drop. And so if you want to reference x, then you would say y, because that's the name of this array. And then this is row column. So this is saying every row in the first column. And then that's divided by, and going back to this equation, it's divided by, well, okay, so 1 plus epsilon x, so then you reference this y, every row in the first column, and then it's multiplied by, so this is x, and then it's multiplied by y, the pressure drop, and so then this is y, every row in the second column. And so then you do the same thing for f. So I just wanted to point that out real quick. And it's the same thing when you plot these. So if you haven't done a lot of plotting in MATLAB, one thing I like to do if I'm plotting a bunch of different things for the same problem is use this subplot. And so subplot is so this is showing that I have one row and 2 columns with plots, and then this is the first plot in that row and column, and then this one's the second plot in that row and column. So for the first plot, I plotted the weight versus, so this is x and y, so the weight versus x conversion, and remember x, that's the every row in the first column, and then I'm saying that I want it to be blue. And then for the next one, I have weight versus weight for x versus the pressure drop, so y, and this is every row in column 2, and I want that to be black. K is black in MATLAB. And then the weight versus this f, and I calculated F here, and then that's red. And so then for this one, same thing. I have the weight versus the rate, which I calculated here. And then in the book, they multiplied the rate by 100, so I did the same thing. So then I can go ahead and plot these. And so this is the plots that they created in the book in this example. And one thing I like about MATLAB is you can go in and edit your plots. So if I go to Tools, Edit Plot, then I can say select this one and adjust it so it looks better. And same thing with this one. And then you can also, like I'm going to add a legend to this because I have 3 different lines. So insert legend. And then, so the blue line is X, or conversion. So we'll do capital X. The black line is the pressure drop. And this is one thing I like about MATLAB. You can put in LaTeX codes. So P divided by P naught. Actually, that didn't work. Oh, okay. So this one I don't think you need the dollar signs. Yeah, okay. And then this one was F. And then you can change the size of this. And you can also play with with these. So let's see here. So if I go to Tools, so what was that again? All right, that was it. So I went to View, no, I went to Edit, Figure Properties, and it opens up this. So then you can click on various things. So for instance, if I click on this one, well, I'll go to this one first. Then I can change the labels here, so FXY. I can change the x-axis, and so this is where you can put in the LaTeX code. So this was M. Actually, maybe you don't need it there either. You need it somewhere. No, it works. Okay, so you can also change your ticks here. So right now this has, I mean the ticks look pretty good on this, but if you had like say 0, 30, 60, you might want to add some more, or if you have 1,000,000, you can take some out so that the plot looks better. And you can also change the font. So right now it's 10, which is actually kind of small, so I usually go in here and make it bigger. So maybe 12, maybe even 14 for this plot. And you can change you can also change the weight, so you can make these bold. No, that doesn't look bold to me. For some reason it's only changing that. Well, anyway, I almost never make these bold anyway, so you can add a title. So this is weight of catalyst versus F, X, and Y. And you can change the colors. So if you want to play with just one specific font, then you can go click on it. That's not what I wanted. All right, so yeah, if you just click on this, then, oh, and this is why, okay, so if I change that, and then I can also change this font, so make the title 14, and change all kinds of things in here, so I think it looks good how it is. And then this one looks kind of small, so I'm going to change it to 14 as well. And the same thing with this one. Oops. 14. Then if I go here, I can kind of do the same thing with this plot. So first of all, since I made the other one 14, I'll make this one 14. I can add a title, so rate versus weight pound m. And normally you'd want to put units on this too, but I'm not doing that right now. But normally you want to put units. So just so you know, like with the rate, you would normally want to put some units. And change this real quick. So then if I want to change this, then yeah, so I clicked on it and then changed that to 14. Change this one to 14. And then I also want to change that. What happened to it? I just deleted it. So the way I can get back to the x-axis is I just clicked on this, and then I have this comes up, and I have x-axis, y-axis, z-axis. So x-axis. Oh, it's okay. So this is where you need to put this in, because I changed it to LaTeX from TeX. And then I'm going to change this to 14. All right. So none of this editing is really required. I just wanted to show you that this is possible with MATLAB. This is one reason why I like MATLAB better than Polymath. I feel like it's easier to make good plots. So then you can see, I want to save this plot. I'm going to save it as a PNG. So and I'm going to save it to the desktop so it's easy. Alright, so then I'll open and find that real quick. Alright, so this is the plots I just made. So this is how you make plots in MATLAB. Recap of how to do this. We started out with, first we wrote down our equations that we need to solve. So the mole balances, the pressure drop, and then everything else is just variables that we need in order to solve these. So the rate, the concentrations, and then in MATLAB we first write a function that calculates the right-hand side, and then we run ODE 45, which is a built-in MATLAB function to solve ODEs, and we call that function and we send in the function that we wrote that calculates the right-hand side. We send in our boundary conditions and our initial condition, or our initial values, and then MATLAB solves that, and then the rest of this is just processing. So we wanted to calculate the rate in this variable f, and then plotted what we calculated.